All right, so we are starting this new unit today, and in this new unit, we're going to be talking a lot about specific types of triangles, specifically right triangles is what we're going to be focusing on. And with that, we have like special right triangles that we'll see eventually. And in special right triangles, you're going to see these square root symbols start to show up. So before we get too far into all of that stuff, we want to spend a day going over with you how we work with square roots in here. Because like on your bell ringer, sometimes when you square root a number, like 25, 49, or 144, you get a whole number to come out, okay? But if you tried to square root like a 5, would you get a whole number for an answer? No, because there's no whole number that you can multiply times itself and get 5. Same with like a 6 or a 7 or an 8 or a 10 or an 11. Like there's some numbers that it works for, but there's a lot of numbers that it doesn't work for. And so in this unit, when we talk about square roots, we're not going to be messing with the decimals for right now. Eventually, decimals will be okay again. But right now, when we work with our square roots, we don't want to see decimals in our answer. We just want to see these simplified radicals. Radical is another word for square root, and I'll probably talk about that every once in a while. Instead of saying square root, I might say the radical, or when I speak about how it's showing up in an answer, I might use the word radical. When it asks this question up here, what does it mean to simplify a radical expression? They're asking, what does that mean to simplify a square root sign? This means that you are going to break down the number under the radical down to non-perfect squares. So non-perfect squares would be those numbers I was just listing off that don't square root nicely. Okay, so before we get into this though, let's maybe review what would be some perfect squares. And we saw a couple of those numbers on your bell ringer today. So I'd like you guys to tell me, going in order, let's start with the smallest perfect square that you know, and let's see how high you can tell me them. So the smallest perfect square would be square root of 1, which is just 1, right? So I'm just going to put 1, because 1 squared is 1. What's 2 squared? 4. What's 3 squared? 9. Remember, when you're squaring something, it means you're taking the number times itself. We're not taking 3 times 2 when you're working with the exponent. That's a common misconception students have. Okay, do you guys know what the next one would be? 16, and then keep going. I want to see how high you guys can go. 100. Anyone know what comes after 100? Do you know the next one? Close. 169. Do you know the next one? It's okay if you don't. They start to get pretty high pretty fast. But the next one would be 196. And the only reason why I remember that is because it's 69 switched around. And then it'd be 225. And then they keep growing, right? You could add this list on for however long you wanted to create it for, okay? If you know like this first chunk up to 100, you're probably sitting in a pretty good position. If you can recognize those numbers I just boxed up there, and you can see that those are all perfect square numbers, you're probably going to be okay with what we're doing today. Chances of you seeing these really high square roots are probably not likely with the stuff that we're going to be doing in this unit, okay? But we want to be able to recognize perfect squares so that we know when we're looking at a number that's not a perfect square that we're going to have to work a little bit with that, okay? So down below, we've got this property that we're going to be using today to help us simplify radical expressions throughout the unit. Okay, symbolically it looks like this. They have the square root and they have a and b underneath that. A and b represent any numbers that I want to multiply together. So I could put in whatever number I want for a and whatever number I want for b. I multiply them and I have that underneath the square root sign. So I could have even numbers, odd numbers, perfect squares, non-perfect squares. What this property says that we can do is you can take those terms if you would like to, if it makes it easier for you, and you can separate them. You can split it apart. So you can put a underneath its own square root sign and you can put b underneath its own square root sign. Here's an example. If I had the square root of 27, so this was my problem that I began with. I can't square root 27 nicely. I'm not going to get a whole number. I would get some really weird decimal. Okay? Remember I said we're not talking about the decimals today. We are talking about the simplified radical. What you would need to do is think about that list that we wrote up there on the top and think about all of those numbers, the 1, the 4, the 9, the 16, the 25, and figure out, is there one of those numbers that goes into 27? 9 does. 9 times 3 is 27. So you can see how they split this down almost into like two factors, 9 and 3. And they're putting 9 in one square root, and they're putting 3 in a square root. But if we square root 9, what do we get? 3, and that's what they have here. But can I square root 3? And are there any perfect squares from that list up above that go into 3? Other than 1. Okay, but 1's not going to change anything for me. But like 4 is too big. So I'm not going to be able to do anything with that, so it has to stay. This is what they mean when they say simplify your square root sign. There's going to maybe be a whole number in the front, and then there's going to be some stuff maybe left behind underneath the square root sign. The only time you only get a whole number is if the number you're square rooting is a perfect square, like the ones we saw in your bell ringer today. All of those came out to be nice, whole, clean numbers. We didn't have anything left underneath the radical sign. There's a couple ways you can approach this. I'm going to show you two kind of methods today, and I'm really going to be okay with you guys using either one. There's a method that I prefer, and so I might lean more towards using that one when I'm doing them with you guys. But if you do the second method, that's okay. The one that I like to do is kind of what I talked through up here, is I look at the number underneath the radical sign, and I try to think about that list that I wrote on the top, and I want to find the biggest number out of that list that can go into what I'm working with. So for this first example, I'm working with 80. Okay, 80 is not a perfect square because it wasn't on my list up here. It skips over 80 on that list that we wrote out on the top. So what I like to do is figure out, okay, out of these numbers, which is the biggest that can go into 80? What did you say? 64? You can take 80 divided by 64? I don't think that's going to work out for us. What did you say? 8 is 8 a perfect square, though? I'm thinking about just this list up here, guys. 4 can definitely go in. Okay, because what's 80 divided by 4? I'm going to come to you in a second, Dash. Okay, 4 times 20 is 80. Okay, but there's a bigger number from that list that can go in. Is that what you're going to tell me? 16. Can 16 go into 80? Do you guys have a calculator? No. You might want to get one out. Someone take 80 divided by 16. Tell me what it comes out to be. 5? So I would take the 16 over the 4 because 16 is bigger than 4, so it's going to save me less work in the future when I'm trying to reduce this. So I'm going to write the 80 like this now. It's the square root of 16 and the square root of 5, not 4, 5. Because 16 times 5 is 80. Now, if you start with the 4, you'd have 4 times 20. You can square root the 4, but you would have to then continue to work with the 20 because the 20 is not a perfect square. I'll maybe show that up here in just a second. Okay, but I like 16 because that's bigger. And then the next number, 5, that's not a perfect square number, but I can't think of any of those numbers from my list that would go into 5. Because 4 isn't going to go in and 9 is going to get to be too big. So what is the square root of 16? 4. That comes out of the square root sign. If you can square root the number, you don't need that radical anymore. And then the 5, we just said we can't square root 5 because you're going to get a weird decimal. I don't want that. And 4 is my smallest perfect square. That could maybe go into 5, but it doesn't work. So I have to leave 5 underneath the square root sign. And I'm going to get this. 4 square root of 5. Now I'm going to let you know the calculators that I have in my room, and if you have one like my calculator, it can perform these square roots for you. You can type in the square root of 80 and it'll give you an answer, okay? However, I am going to want to see the work, okay? I need to see your thought process behind breaking down the square roots. I'm not going to accept answers where you just type it into your calculator and give me what it says. That'd be an excellent way to check how you're doing your problem if you're doing it correctly, okay? But I also want to see the thought process. How did you get there? How did your calculator get to that number? Okay, we need to understand how it's working and why it does what it does. That's method number one to get to your answer. I want to back up a second because someone had said originally 4 goes into 80. So I'm going to write that over here. I would have the square root of 4 and the square root of 20 if I used 4 instead. Because that also works. What's the square root of 4? 2. And then that square root of 20 would still be underneath here. But that's not the answer that I got. Okay, so that tells me over there, yes, 4 works, but you're not done with the 20. Can you guys think of a perfect square that goes into 20? From that list on the top, 4, 9, 16, 25. Does one of those numbers go into 20? 4 does. So this 20 could be rewritten as 4 and the 5. Well, what's the square root of 4 again? 2. I already have this 2 out here, so I'm going to have to multiply them together, and then the 5 stays. What do I get for a final answer? So did I get the same answer? Yes. Is that more work? Yes. So I wouldn't advise that you go that route. That's why I'm telling you, find the biggest perfect square from that list up above. So even if like a 4 or a 9 works, maybe test some of those other numbers, like the 16, the 25, the 36, and see if any of those work, because it's going to save you from having to do extra steps. This took me way longer than this one did. Okay? Now, this is how I learned how to do it. So, like, I'm just going to say this is what I would be doing. Okay? When I was in your guys' shoes in school and I was learning how to do this, this is how I was taught. You find the biggest perfect square that goes into the number. Okay? There is another method that you could use, though, and this is what I want to show you so that if you like the second method better, you can use it. I'm going to erase this for right now because I need some room. Do you guys know what a factor tree is? You've done factor trees before.
Oh, yeah.
I'm sure you have. You do the little branches off of it like this. And you think, what are 2 numbers that multiply to 80? Any 2 numbers. 10 and 8. I'm trying to get down to prime numbers. Prime numbers would be anything that can only have 1 in itself as factors. 10 and 8 are not prime. What are some numbers that can go into 10? 5 and 2. Those are both prime numbers because I can't break those down any farther. How about 8? 2 and 4, or 4 and 2, and then 4 becomes 2 and 2. Okay, then what I do is I'm going to look in all these prime factors. So 5's prime, all these 2's are prime. Okay, so I'm just circling your prime numbers. To do the square roots, you look for pairs of 2. You look for groups of 2. So I see these 2 2's, and I see another pair of 2's. Those can go together. When you have a pair, these numbers are going to be able to come out of your square root sign. So those 2 individual 2's are going to pop out. So this is another 2 times 2. Does the 5 have a partner? No. So the 5 can't come out. It has to stay underneath the square root sign. So these come out, and you multiply them. So what's 2 times 2? 4. And the 5 stays underneath. So you still get 4 square root of 5. That's still the same answer that I got originally. You can do either method. Some students like the factor trees because they like to find the groups of 2 and they like to pair it up like that. Some of you will probably prefer to use that list of numbers that we have on the top of the screen. Okay, either method works though. Because I was taught this, I tend to lean more towards that one. I also just feel like it's a little bit faster because I'm just doing one thing of division versus trying to work with all these branches for my factor tree. Okay, let's do another one here. Let's come over here to this one that says 6 square root of 90. You can factor tree this, or you can think about a perfect square. Okay, so I want you to think about that number 90 and then look back at that list of numbers on the top of your page. What's a number that can go into 90? 9 can. I would even just think like this would become 9 and a 10, right? Because 90 divided by 9 is 10. Are any of those numbers from your list able to go into 10? No, 4 can't go into 10 nicely, 9 can't go into 10 nicely, and then 16 gets too big. So 9 is probably the biggest perfect square. So I'm going to go ahead and use that. So I'm going to rewrite this 90 as the square root of 9 and the square root of 10. Now notice that there's a 6 sitting in the front here. The 6 is just going to tag along. Okay, we're not going to disappear. We're not going to make the 6 disappear. We're not going to change it by any means. We're just going to have it kind of attach itself to the rest of the problem. Now, what's the square root of 9? 3. So this square root of 9 becomes a 3. The 6 comes down, and the square root of 10 has to stay. All right, now should I write 63, or what do you think I should do with the 6 and the 3? You got to multiply them. Don't just write 63. What is 6 times 3? So this becomes 18, and the 10 has to stay. I can't do anything with this number. I can't square root it, and there's no nice perfect square that goes into 10. So you're done. This is your answer. Does anyone have questions on these first two? Okay, let's try another one. Okay, this next one here says the square root of 12 and the square root of 3. Who's got a thought on what to do? Square root of 4. Okay, so I'm going to write what he said. He's breaking 12 down into the square root of 4 and the square root of 3. Okay, that's what the 12 becomes. This other square root of 3, can we do anything with it? No, so I'm just going to attach it here. What would you do next? Square root of 4 is 2. Okay. Since the 3's are both underneath square root signs, we can put them together because they're like terms. Kind of think about like variables. If you had lots of x's, you can put all your x's together. If you have things underneath the square root sign, you can multiply their numbers together. So I've got 3 and 3. What is 3 times 3? 9. So this becomes the square root of 9. Are we done? 2 times 3, because the square root of 9 is 3. What's my final answer? Was there a faster way I could have done that problem? Do you see it? No. Think about what we did here to get the square root of 9. Could we have done that from the very beginning? They're both under square roots, aren't they? So you can take 12 times 3. What is 12 times 3? So this is actually the square root of 36, which you guys all know is 6. Is that faster? Does that always, it's not always going to work that way, okay? You're not always going to be able to like multiply and get a perfect square and everything's grand. Okay, but that might be something that you want to look into before you go about that route. See what happens if you put those numbers together. It might make it easier to work with that number. Or if you have two things underneath square roots and you can't think of any way to break them apart, maybe you will have to multiply them together in order to do something with it. Okay? All right, let's take a look at this last one on our page here, square root of 35. If you're using my method, are there any perfect square numbers that go into 35? No. Okay, if you think about the factor tree method, what are two numbers that multiply to 35? 5 and 7. So if you're thinking this way, 5 and 7, those are both prime numbers. There's no group of 2. So I can't think of a perfect square that goes into 35. I can't do anything with my factor tree. So the square root of 35 is already simplified. There's nothing I can do with it. So we're going to just leave it as is. There are some numbers that simply nothing can be done. You can't simplify anything. You can't do anything more than just leave it the way it is. Okay, we're going to get you guys your homework, but I'm going to grab just a couple from your homework and do them with you just to make sure we're feeling okay about this stuff. So will you just pass that out really quick? I'm going to pull your homework up here on the screen. Okay, I'm just going to grab a couple because I want to make sure you guys are feeling okay about this since we only had a few examples. I'm going to do number 2 with you. So let's start there. And when I say with you, like I'm going to guide you along, but I really want you guys to be doing some of the thinking here. So let's start here, square root of 72. Okay, if you need to, on the top of your guys' homework page, write out that list of perfect squares that we had. 4, 9, 16, all those numbers. You don't have to write them all out. Remember I said if you know up to like 100, you're probably sitting in good shape. Okay, but we're using that to kind of help us along here. We're using that list of numbers to maybe help us figure out how to break these apart. All right, so let's come back down here to that 72. Is there a number from this list that we could take 72 divided by?
36.
36? Because 72 would be 36 times what? 2. So I'm going to rewrite this as the square root of 36 and the square root of 2. What is the square root of 36? 6. And what happens with the 2? Has to stay, right? Nothing happens to it. It just attaches to the 6. There's your answer. Okay, let's do one more. Let's jump down just right underneath it to number 6. Let's skip over. You guys can do 4. Let's skip over 6, or go to 6, I mean. Let's go here. Square root of 150. Can you think of a number from up above that would go into 150? And if you're not sure, use a calculator to guess and check your way through it. Start taking 150 divided by some numbers. 25 times 6. Okay, so I'm going to rewrite this as the square root of 25 and the square root of 6. What else do I need, though, here?
10.
The 10. That's got to tag along, okay? It's like playing third wheel right now. All right, what's the square root of 25? 5. Can I do anything with the 6? So what is your final answer? Good, 50. How did we get the 50? You got to take the 10 times the 5. Okay. All right, let's flip over to the back. Because we didn't have any in your guys' notes that talked about this. We didn't have any that dealt with division. So I want to go over just a couple here so that you guys kind of know how to handle these ones. I want to start, we're going to do 13 and 15 together. I want to start with 15 though. So when you guys look at those square roots, is there anything that you think automatically you should do? Yeah, make that bottom of 4 because it's a perfect square. So I'm going to rewrite this as the square root of 12 over 4. Okay. When we have a fraction, we are never allowed to keep a square root in the denominator. It's just like one of the rules that we have in math. Like you can't keep denominators in the fraction. It's kind of like bad form in the math world. So if I can square root it like that one, I'm taking care of that problem. Like I don't have a square root anymore in my denominator, okay? But now, can I break the 12 down at all? Is there a perfect square that goes into 12? Does 4 go in? 4 times what is 12? 3. So I think we can rewrite the top as the square root of 4 and the square root of 3. And this is still all over a regular 4 now. And what is the top going to say? 2 square root of 3 all over 4. Now these whole numbers, you can reduce them. If they have anything in common, you can take stuff out. So this would just become square root of 3 over what? Not 1, 2. Because this becomes a 1, this becomes a 2. Okay, let's go back up to number 13, because this one's going to be a little different. This time, the bottom is the square root of 27. Unfortunately, we can't just square root that. Okay, the last one was a little bit nicer because of the number that they gave me on the bottom. I don't have that for this one here. Okay, I have to work with that 27 a little bit. What's a perfect square that can go into 27? 9. So how would you guys rewrite the denominator? Good, 9 and 3. And the top would still just be 3. What's the square root of 9? 3. So I have square root of 3 on the top. The 9 becomes a 3, and then we still have a square root of 3 here. Is there anything you think we could get rid of right now? The square roots can actually disappear, because just like we had like terms with the 2 and the 4 on the last one, if they're both underneath square root signs, you can reduce them. Okay, so the 3's are both the same. It's like taking a number divided by itself. They're gone. How do I write my final answer here, though? 1/3. Where'd the 1 come from? Yeah, the top. This doesn't just go to a 0, right? Anytime you reduce, it doesn't just disappear. It becomes a 1 when you cancel it out. So this is 1/3. All right, I know I said I was going to do 2. I'm going to do one more. Sorry, I lied. I'm going to go to number 18. This is the last one I'm going to do with you guys, and then I'm going to give you time to work. All right, we have 2 over the square root of 5. Can you do anything with the 5? No? 4 doesn't go into 5, right? And 9 gets too big. Okay, so I can't break that down. There's not going to be anything that just cancels away on this one. But again, I can't leave square roots in the denominator. So I need to multiply by the issue. And when we multiply, you have to do it to the top and to the bottom of your fraction to keep it balanced. So we're going to multiply the top by a square root of 5 and the bottom by a square root of 5. On the top, you can't put the 2 and the 5 and make a 10. Why can't I put them together? Yes, one's got a square root, the other one does not. So they have to stay separate. So I'm going to leave that 2 square root of 5. What happens on the bottom? Square root of 25. Which is what? 5. So 2 square root of 5 is still on the top, all over 5. Can you reduce anything? No. Why can't we reduce these? Yeah, they're both different from each other. This one has that radical sign. This one does not. So you're done at this point. Okay. Just real quick, I want to point this out to you. Look at this. We had square root of 5 times square root of 5. What did the bottom just end up becoming? Well, it became 25, but then it just became a 5. Anytime you guys take a square root times itself, the number is just going to pop out of the radical. That's a little shortcut that you can maybe start to recognize. Anytime you take like square root of 3 times square root of 3, the answer is 3. Square root of 7 times square root of 7, the answer would be 7. Okay, so if you see something like that, you can kind of shortcut your way. You don't have to give me that step in the middle if you understand what's going to happen there. All right, I'm going to give you guys the rest of time here to work on these problems. And if you get stuck on some, I know we don't have a ton of time left. We'll go over questions that you guys have tomorrow on these square roots, okay?